So please ask all your friends to attend. Otherwise, I'm going to download the attendance only after 10 minutes. So whoever will join after 10 minutes, they will not get the attendance. Okay. Otherwise, people, start joining towards the end. So anyway, when we download the attendance, there the time is mentioned at what time you joined and at what time you have signed out.
Sir, hello.
Yes, Ravindra, please tell me.
सर मैं जगवीर बोल रहा हूँ सर, वो ज्वाइन नहीं हो पा रहा, मैं अपने फोन से पता नहीं टीम्स पे ज्वाइन नहीं हूँ, इसलिए मैं इसके साथ ज्वाइन कर रहा हूँ सर।
क्या नाम है? आप अपने फोन से ज्वाइन नहीं कर पा रहे हो तो आप, क्या नाम है आपका बताओ? आई विल इंक्लूड यू।
जगवीर सर, मतलब मैं टीम्स पे
जगवीर,
ज्वाइन नहीं हूँ, पता नहीं।
आई एम कॉलिंग यू ऑन टीम। जगवीर मीना ना?
यस सर, यस सर।
तो आई एम कॉलिंग यू, प्लीज ज्वाइन बाय योर नेम, otherwise your
यस
attendance will not be marked, somebody else will.
यस।
I already called you
ओके
on
सर,
Teams. देखो ज्वाइन कर पा रहे हो कि नहीं?
ओके सर, आई विल ट्राई।
So we will wait for 1 or 2 minutes and then we will start. Okay. So with the class of 188 student, only 56 is joining. That is not good.
सर वो शो कर रहा है कि आप मेंबर नहीं हो, मतलब टीम्स पर, मतलब आवाज नहीं आ रही सर, आपकी वजह आप म्यूट हो।
Are you able to join, Jagveer? If you are
नो
opening
सर।
two teams, if you are opening two teams from the same device, you will not be able to join.
ओके,
Okay.
यस सर, शायद मेरे दो अकाउंट है, वैसे एक ही पी का है, मतलब मेरी ब्रांच चेंज हुई शायद उसकी वजह से।
So if you are not able to join, no problem. You remind me that you have attended. I remember your name. Okay. You join from the
Okay.
same account, but remind me. Okay. All right.
Oh,
I will
okay, sir.
mark your attendance. Okay, so I think we are already 5 minutes now. Let us start with today's class. And before we start today's class, let me first apologize for doing this class online. In fact, I am here at IIT Delhi, but IIT has uh, nominated me to attend one course, and that course is happening in the LSC. So I am kind of enjoying the student life these days. From 9 to 5 there are the classes which I am attending, and I'm extremely sorry for not doing your classes at a regular slot. And I hate to take the online classes because that learning happens only in the physical class. Online class, people they only join, and whether they are attend they are attentive or not attentive, whether they are listening not listening, uh, really we don't know, isn't it? And I want students to learn, but unfortunately I am not able to see whether they are getting anything from the course or not. Okay. So please, I request all the participants to be lively and ask as many questions as possible. And I will be happy to answer any of your questions, even if these questions are not relevant. If even if these questions are silly, I don't mind. Please ask the questions. We have that habit of asking the question, and that will also keep me on the toe, isn't it? If you ask more question, I will be more prepared to answer your questions, isn't it? It is, this communication should not be one way, it should be two way, isn't it? So I am again apologizing for not taking the class in the physical classroom and doing it online, primarily because from 9 to 5 I am attending other classes, and extremely sorry. Uh, but from the next week onward, we will have all our classes done in a physical mode. One more announcement is we are having a quiz. Remember, we are having a quiz one on 20th, that is Sunday, from 2 to 4, isn't it? One more announcement is there. We have not done the tutorial on Monday, and also we are likely to miss the tutorial on Friday. Okay, so this tutorial number 9, we will do it physically on some day. I will convey the date later. Okay, all the regular classes probably I will have slightly extended class today, and also I will have slightly extended class tomorrow. So we will not have a class on even Friday. Okay, is that okay to everyone? Please, please tell me if there is any problem uh, with the time or any other concern. Yes, Tuhin, please ask the question.
So tomorrow I have some commitments after 8:30.
Okay, so 7:30 to 8:30. Anyway, we will have a class. At max, we will extend by 10 to 15 minutes, not more than that. Okay.
That's fine, sir.
All right. Thank you, Tuhin, for accommodating the request. Is there any concern, anyone? Okay, so if no concern is there, let me share the slide. Please ask the question, as many questions as possible. Okay. If something is not clear, please don't hesitate to ask the question. Let me just open the slides. Is the slide visible to everyone?
Yes, sir.
Let me just start from where we have left in the last class. Okay, so this is the slide where we have left in the last class. Okay, so remember in the last class what we started looking at? We started looking at how different controllers are going to impact, or how a feedback loop is going to impact the overall response of the process, isn't it? We might be having a first order process or a second order process, but how uh, the response of that particular process in addition with the feedback loop is going to be. Okay, so this is what we have seen, right? A typical feedback loop is uh, like this, isn't it? Process can be first order or second order, and depending on the controller, what will be the overall response of the process? That is what we tried to understand, and we have derived this generalized expression, isn't it? So overall response of the process when the process is getting controlled by using a feedback loop, then if there is a change in the set point, then my overall transfer function with respect to the change in the set point will be the transfer function associated with the servo problem, which will be given by all the transfer functions in the forward line divided by all the transfer functions in the loop plus 1, isn't it? So if I'm interested in how y dash will change if there is a change in YSP, isn't it? So YSP is the change in set point. If there is a change in set point, how my Y dash is going to change? If I am looking at this particular problem, the problem is referred as a servo problem. And in a servo problem, this is the input and this is the output. So between output and input, how many transfer functions are there in the forward line? GC, GF, GP, isn't it? Divided by 1 plus all the transfer functions in the entire loop. So that becomes GC, GF, GP and GM. So that is what we are getting here. So Y dash S, how the output is changing with respect to YSPS. The transfer function given here is this GPS, GFS, GCS divided by 1 plus GP, GF, GC and GM, isn't it? Similarly, for a regulatory problem is a problem where I am looking at how my output is going to change when there is a change in the disturbance variable. So between the output and this input disturbance variable, what are the transfer functions in the forward line? Only the GD is there. That is why in the numerator here only the GD is there. And in the denominator again 1 plus multiplication of all the transfer functions. So this is the overall expression we are looking at in the different context in this particular example, isn't it? So this is the generalized expression we are looking at, and this generalized expression then we have tried to understand in the context of tank system. Then also we have tried to understand the same generalized expression in the context of stir tank heater, isn't it? Correct. And based on that, we have identified what is GD, GP, GF, GC, GM, etc. This is what we have done in the last class before the mid-sem break. Okay. Again, in the last class, what we have done is if there is a process which is, let's say, a first order process, if there is a process which is a first order process and the controller is a proportional controller, and for a time being we are neglecting the dynamics of the measurement unit and the final control element. In that case, how my response is going to be when there is a servo problem or a regulatory problem? This is what we have seen. So what we said is whenever we are having only a proportional controller, what we get is we get a first order process itself. Our response is, if you look at this particular expression here, our response remains first order, but my system response becomes faster whenever there is a feedback loop. That is what we have seen in the last class, isn't it? So if I compare this particular expression with usual expression of the first order process, you can see that the tau p dash is a lower value than the original time constant of the process, because original time constant of the process is divided by 1 plus kpkc. So clearly kpkc is a positive number, so this tau p divided by 1 plus kpkc is a lower value than the actual time constant of the process, tau p. So clearly this tau p dash is a lower value than tau p, and therefore the system response becomes faster. That is what we have seen. So process remains first order, but the speed of response increases. Again, if you wanted to calculate what will be the offset, offset is nothing but what? Offset is nothing but the new set point minus the ultimate response. So if you calculate that, that comes out to be 1 upon 1 plus kpkc. So clearly we will have a non-zero offset whenever we are having a proportional controller. That is what we have concluded, isn't it? And The same thing happens even if we are looking at a servo problem or a regulatory problem. In a servo problem also we get the offset which is 1 upon 1 plus kpkc. If we are having a regulatory problem, we get a minus kd divided by 1 plus kpkc, isn't it? That is what we have obtained. Then we have again discussed that whenever we are having a pure capacitive process, that means 1 by s term is there in the transfer function. In such cases, the servo problem gives a zero offset, whereas a regulatory problem gives only 1 minus 1 by kc. So clearly this type of equations we get whenever we are controlling the level of the tank. And that is the reason why proportional controller is popular in a level control. Why? Because if you are looking at a servo problem, you get a offset equals to 0. And if you are looking at a regulatory problem, you get a offset which is equals to minus 1 by kc. And having reasonably higher value of kc, you can actually decrease the offset to a reasonable value. And that is the reason why in a tank control system, typically whenever you are controlling the level in the tank system, the popular controller used is a proportional controller. Up to this we have seen in the last class. So is it clear to everyone up to this, whatever we have done in the last class?
Yes, sir.
Okay. Again, towards the end of the last class, we started looking at how my second order system will respond to a feedback control loop with proportional controller. That also we have done, but again, we will summarize it a little bit more so that there is a continuity of what we are doing. So again, let's assume that my process is a second order process. Second order process will have a transfer function of kp divided by tau square s square plus 2 zeta tau s plus 1. And again, we are assuming that there is a negative feedback system and negative feedback system with proportional controller. So that means gc will be equals to kc, whereas the transfer function of the measurement unit and the transfer function of the final control element we are taking as 1. So what we are actually assuming here, we are assuming that the dynamics of the measurement unit and the dynamics of the final control element we are neglecting here. Okay, so now with this, our generalized expression is what? Our generalized expression is this. Ys is given as gp gf gc divided by 1 plus gp gf gc gm ysps plus gd divided by 1 plus gp gc gf gm into d of s. Then this is the generalized expression I am having. Now if I take the example of servo problem. In a servo problem, this part is 0, isn't it? In a servo problem, the only input variable is a change in the set point. There is no change in the disturbance variable. Remember, all these variables are represented in a deviation form. So clearly, if there is no change in the disturbance variable, this term becomes 0. And the only term remaining in a servo problem will be what? Ys will be given as gp gf gc divided by 1 plus gp gf gc gm into ysps. Correct. This is the expression we are having in a servo problem. Now putting this gm gf equals to 1 and gc equals to kc, what we are going to get? We are going to get ys is given as gp kc divided by 1 plus gp kc into ysps in a servo problem. Only this much part will be remaining in a servo problem. Now in this particular expression, replace this gp by the second order transfer function. So with that we get ys is equals to kp divided by tau square s square plus 2 zeta tau s plus 1. So this is nothing but gp into kc divided by 1 plus gp is nothing but the same kp divided by tau square s square plus 2 zeta tau s plus 1 into kc, and outside there will be ysps. I can simplify this particular expression. So I can divide numerator and denominator by tau square s square, multiply the numerator and denominator by tau square s square plus 2 zeta tau s plus 1. So with that, what we will have? We will have only kp kc in the numerator. This term will get cancelled out. And similarly, in the denominator, we will have only tau square s square plus 2 zeta tau s plus 1 plus kp kc into ysps. This is what the expression we are expected to get for a servo problem. Do you all agree with me? Yes or no?
Yes.
Okay. Now in this particular case, this expression is not in a standard form. It is not in a standard form. So what typical method we do in order to make the expression in a standard form? We are going to divide numerator and denominator by 1 plus kp kc, isn't it? So if I divide that, what I'm going to get? I'm going to get kpkc divided by 1 plus kpkc, and the entire term divided by tau square divided by 1 plus kpkc into s square plus 2 zeta tau divided by 1 plus kpkc s plus 1 into ysps. Now this particular expression is in a standard form. I can represent this entire expression as kp dash divided by tau dash square s square plus 2 zeta dash tau dash s plus 1. There is a 1 missing. There should be a 1 here. Okay, plus 1. Is that clear to everyone? Hello?
Yes.
Yes, sir.
Now, just a minute. I will just write 1 here so that it is clear. Is it clear now to everyone? Hello?
Yes, sir. Yes, sir. Yes.
Okay, so now this particular expression is in a standard form. This particular expression is in a standard form. So I can equate what is tau dash, what is zeta dash, and what is kp dash. So tau dash in this case comes out to be tau divided by under root 1 plus kp kc, because this tau dash square will be nothing but what? Tau square divided by 1 plus kp kc, isn't it? So tau dash will be equals to tau divided by under root 1 plus kp kc. Similarly, zeta dash will be, zeta dash comes out to be zeta divided by under root 1 plus kp kc, and kp dash comes out to be kp kc divided by 1 plus kp kc. This is what we are going to get from this particular expression itself, isn't it? Now we can look at each of these quantities little bit in more detail. If I look at tau dash, and if I compare this tau dash with this tau, what we are concluding? We are concluding that this tau dash is a lower value than this tau. Do you all agree? Yes or no?
Yes.
Yes,
Because
sir.
this kpkc will be always positive. So 1 plus kpkc is always greater than 1, isn't it? That means tau divided by under root of this entire term 1 plus kpkc, this entire term is going to be less than tau dash, isn't it? So clearly tau dash is lower than tau. So what it means? What is tau in a second order process? What is tau in a second order process? What was the physical significance of the time constant of the second order process? Anyone? Anyone?
Time to reach its limited value.
No. That is for the first order process. Remember, time constant in the second order process is nothing but the natural period of oscillation. It is nothing but the time period between two peaks. Do you all agree with me or not? Yes or no?
Yes.
That is what the physical significance we have seen. And I have said at that time, the physical significance of the time constant in the first order process and the physical significance of the time constant in the second order process is not same. They are different. Okay, they are not same. Okay. Now, zeta. Here zeta is also becoming lower than the zeta of the actual process. Remember here tau and zeta are nothing but what? These are nothing but the time constant and the damping factor of the original process. But when I am having a feedback control loop, in that case this tau, in that case the time constant comes out to be tau dash and the damping factor comes out to be zeta dash. And both tau dash and zeta dash are lower value compared to their actual process, isn't it? So here zeta dash is also going to decrease. So what it means? It means that I might be having my actual process which is over damped, but because of feedback loop, my actual process which is over damped, isn't it, may give me under damped response if there is a feedback control loop. Do you all agree with me or not? Make sense or not? So see this zeta dash, which is nothing but the damping factor of the overall process when I have applied the feedback loop. When I have applied the feedback loop, my zeta dash comes out to be lower value than zeta. This zeta might be greater than 1 and the process might be over damped. But when I'm calculating zeta dash might be lower than 1. So what it means? It means that my actual process was over damped, but because of feedback loop, the response which I am getting is under damped. Do you all agree with me or not? Hello?
Yes.
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 So that is what we are concluding. And the third conclusion here is what? My process is, my original process was second order, but my order of the process is not changing when I'm having a feedback loop with a proportional controller, Okay. When I'm taking a feedback control system with a proportional controller, and if I'm neglecting the dynamics of the final control element and the measurement unit, the order of the process remains the same. It is second order. It is not increasing the order, isn't it? The order remains the same. The only change I am having is the gain decreases, the process gain decreases, static gain decreases. Also, both natural period and the damping factor decreases. Okay, that is what the conclusion we are having. Now let us take, let's say there is a step input given to the process. Remember, this is the transfer function we have obtained. A step input is given in a set point. So if I give a step input in a set point, what it means? It means that YSPS is nothing but what? It is nothing but 1 by S. Do you all agree? So this YSPS will be 1 by S. That is nothing but step input of magnitude unity is given in a set point. Correct. So with that, this is the YS expression we have obtained. I can find out what is the value of YT directly. I can directly get YT by applying the final value theorem here. I can apply the final value theorem and I can calculate y at t tends to infinity, that is given as limit s tends to 0, SYS. Now this S and this 1 by S will get cancelled out. So what I will left with? I will left with this entire equation without this 1 by S, and then I have to put S equals to 0. If I put S equals to 0, here also 1 is missing. Okay. So here also I will, just a minute. Here also plus 1 is required. Is it clear to everyone? So what we will left with? We will left with only Kp dash if I put S equals to 0 in this particular expression. Do you all agree with me or not? Hello?
Yes, sir.
So I request the participants to, please, respond to the questions and also ask some interesting questions. Okay. More you will ask, I will be really, really happy. Okay. Please ask the question, because real learning happens only when you ask the questions. This is what I have seen over the period. If you ask more question, more and more learning is there. Okay. But if you keep mum and, will not ask, it just becomes monotonous. Okay. All right. So now in this case, if we apply the final value theorem and calculate what will be the ultimate value of y, ultimate value of the y comes out to be Kp dash. Kp dash is nothing but what? Kp Kc divided by 1 plus Kp Kc. Now I can calculate offset. Offset is nothing but what? New set point. So new set point is what? Earlier set point was what? YSP is what? YT is what? YSPT is what? It is 0, because YSPT is calculated in a deviation form. It is, earlier it was 0, but when you have given a step input, your set point changed by a magnitude of 1. So what will be the new set point? Just 1, isn't it? In a deviation form. So 1 minus Kp dash. So 1 minus Kp dash is 1 minus Kp Kc divided by 1 plus Kp Kc. So that means you are going to get 1 upon 1 plus Kp Kc. And this is not 0. This is not 0. So what it means? It means that with a proportional controller, even if you are taking a first order process or a second order process or even higher order process, any order process except the pure capacity process, the first order process will always give you offset, and that offset is not 0. Do you all agree? Do you all agree with me? Yes or no? So whenever we are
Yes.
having a proportional controller, with a proportional controller, unless the process is pure capacitive process, it will always give you a offset, isn't it? You will not reach to a ultimate value at all whenever you are having a proportional controller, isn't it? I can approach to the value, offset value equals to 0 if I increase the value of Kc, but I will not be able to increase the value of Kc beyond a limit. Why? Because if I increase the value of Kc, it leads to a stability problem, and therefore I have to be conservative in selecting the value of Kc, isn't it? So that means what? Whenever I am using a proportional controller, I will always have a offset unless the process is pure capacity. Do you all agree?
Yes, sir.
Okay, so up till now we have only concentrated on the proportional controller. Let's move from the proportional controller to a integral control action. See, so far we are only looking at what impact a proportional action is going to add in my feedback response, isn't it? Correct. Let's look at what impact my integral action is going to add in the process response. Okay, so that's what we are going to see. So in this case, this is the same thing. Hello, is my slides visible?
No, sir.
No, sir.
Let me again go back to the slides. Is it visible now?
No, sir.
Yes, sir. It's a black
Slides are
screen.
not visible.
Black screen.
It's a black
Black
screen.
Yes, sir.
Let me just see why it's a black screen. Is it visible now?
Yes,
Yes.
sir.
Yes, sir.
Okay. Okay. All right. Okay. So now the same thing is written here. You can see that as I increase the value of Kc, my system response actually becomes, whenever I'm looking at uh, uh, a first order or whenever I'm looking at a second order process, and if I increase the value of Kc in a feedback loop, you can see that my process can be initially overdamped. And as I increase the value of Kc, my process becomes overdamped to underdamped. If I further increase the value of Kc, my process becomes even more underdamped. So as the value of zeta decreases, you can see that the system response is going to become faster, but that will lead to the oscillations. And as the value of Kc increases, my offset tends to decrease. So here you can see that the lower value of Kc1 is giving me a higher value of offset, but as the value of Kc increases, my offset is actually decreasing. So and I'm moving close to the ultimate response, but I will not reach to the ultimate response at all whenever I'm using the proportional controller. Is that clear to everyone? Isn't it?
Yes.
That is what is written here. The same thing what we were discussing. Is that clear to everyone? So you can see that as the value of Kc increases, you can see that your offset actually decreases. And you are moving closer and closer to the ultimate value. Remember here, this dashed line is nothing but the ultimate response. So I am reaching closer and closer to the ultimate response as my Kc value increases. So here you can see that the Kc1 is smaller than Kc2 and Kc2 is smaller than Kc3. So higher value is Kc3. So for higher value, your speed of response increases. But then increase in the speed of response actually comes with the cost of oscillations. So here with a higher value of Kc3, my oscillations are actually increasing compared to when Kc1 is smaller. Is that clear? Hello?
Yes.
Yes, no, please say. Hello?
Yes.
Yes, sir.
I request most of the students to ask the question and be in an interactive in the class. Otherwise, it is kind of, I am only teaching to a screen, and that is the reason why I don't like this online teaching, because I don't get to see whether you are actually enjoying the class or not. So please ask as many questions as possible. I want you to make my life slightly more difficult than what is now. Okay, if you ask me more questions, I will be compelled to study more. Okay, is that clear to everyone? Please say.
Yes, sir.
Yeah.
It's not inspiring any confidence, man. Only one or two students are saying. Maybe more students should say. Is it clear? Not clear? Do you want me to change something? Hello?
No,
Can
sir.
you slow down the
No,
speed a little bit,
I
because the paying attention is becoming harder when it's on screen.
That's really good. Okay, I like that. Okay, so what we are trying to say here is, okay, so this is the expression we have obtained. Now in this particular expression, what is tau dash? Tau dash is the new time constant, and this tau dash is nothing but the time constant of the overall process, including the feedback loop. What is tau? Tau is the time constant of the process only. It is not including the feedback loop. So this tau is a time constant of the actual process, whereas this tau dash is nothing but the time constant of the entire feedback loop, which includes the controller and which also includes the feedback loop. Okay. Now this tau dash is going to be lower than the actual value of tau. So that means what? What is the physical significance of the tau? It is nothing but the natural period of oscillation in case of a second order process. Since we are talking about the second order process, this tau dash is decreasing. That means the natural period of oscillation is decreasing. That is what it means. Similarly, zeta dash is also decreasing compared to the actual value of the zeta for the process. So that means originally my process might be overdamped, but with a feedback loop, I might get an underdamped process. And also the steady state gain, which is Kp dash, is also decreasing here. Now, in this particular case, what we are saying is, let's say if I increase the value of Kc here, what will happen to tau dash and zeta dash? If I increase the value of Kc, what will happen to tau dash and zeta dash? It will become even lower. It will decrease, isn't it? Both tau dash and zeta dash will decrease. Correct. So that means what? I might be having an overall response which is overdamped with a value of Kc equals to just Kc1. But as I increase the value of Kc1 to Kc2, let's say, what will happen to this zeta dash? Zeta dash is going to become even lower. And lower is the value of zeta dash. What it means? When the damping factor decreases, what impact it adds on the response? My response becomes faster. But that faster response comes with a cost of oscillations. So you can see that as I increase the value of Kc from Kc1 to Kc2, my response becomes faster, but then I had a oscillation. Again, if I increase the value of Kc from Kc2 to Kc3, then what will happen? My response again becomes faster, but then I am having more oscillations. One more thing to note down here is, as the value of Kc increases, also my offset is decreasing. So when Kc value is higher, then I am having a higher offset. If I further increase the value of Kc, I am getting a lower offset. If I further increase the value of Kc, I will get even lower offset. Isn't it? I will get a zero offset only and only when this Kc becomes infinite. And that choice I do not have. Okay, so that means what? Whenever I am having a first order or even a second order process with a proportional controller, I will always have an offset. I will never get a zero offset in this particular case, unless the process is pure capacitive. I will get a zero offset only in the case of pure capacitive process, otherwise not. Is it clear now? Somebody asked the question. Is it clear?
Yes, sir.
Okay, so who asked that question? Please tell me your name. Hello? Who asked the question?
Abhinav.
Gaurav?
Abhinav.
I'm sorry, I'm not able to hear. What is your name?
Abhinav.
Abhinav.
Yes, sir.
Is that correct? So Abhinav, thank you so much for asking the question, and all students should ask the question. I'm really thankful to you. In fact, I request all the students to ask the question like Abhinav. Okay, can we go ahead, guys?
So what is the difference between KP and KC?
Very good. So Kp is a gain of the process. Remember how we have represented the process? Let me go back. So we have represented the process. See, the transfer function of the process is given by Kp divided by tau square s square plus 2 zeta tau s plus 1. So what is Kp? Kp is the gain of the process. And what is Kc? Kc is coming from the controller transfer function. So Kc is nothing but the gain of the controller. So Kc is in your hand. Remember, Kc is the parameter which a user has to set. So this is the parameter which you can change, but Kp you cannot change. And that is the reason in this particular plot, we are looking at the variation in Kc and not the variation in Kp. Is it clear to you now?
Yes, sir. Got it. Got it.
Because this is the parameter which is in your hand. You can change this parameter. Kp will not be, you will not be able to change the Kp. Why? Because that Kp is coming from the model equation of the process. It is coming from the concept or the physics of the problem. You will not be able to change Kp, but you will be able to change Kc. Why? Because this you have to enter the value. Make sense to everyone?
Yes,
Hello?
sir.
Okay, so can we go ahead? Is there any more question? Hello? Is it clear to everyone?
No. Yes, sir.
Okay, so let's
Yes,
move
sir.
to a next point. So remember, so far we were only concentrating on how the proportional action is going to impact my response. But I'm also interested in understanding how my integral action is going to impact my response, isn't it? So let's look at how my integral action is going to impact the response, isn't it? So again, we are starting with the same expression. This is the same generalized expression we are looking at, isn't it? Again, we are also taking gm and gf equals to 1. So what it means? We are neglecting the dynamics of the measurement unit and the final control element, isn't it? And unlike the previous case where we had the controller, proportional controller, now we are only looking at how my integral action is going to impact. So now what will be the transfer function for the integral action? Only the integral action I'm saying. When I'm having a PI controller, what is the transfer function for the PI controller? Anyone? What is the transfer function for the PI controller? Proportional integral controller. That we have already seen.
KC.
It is
KC to
Kc multiplied by 1 plus 1
Error.
upon tau is. Correct?
Yes, sir.
But let's say that is PI controller. But let's say if you are having only the I controller, there is no P. Only the I controller is there. Integral controller is there. What will be the transfer function?
1 by I.
Kc divided by tau is. That's it. Correct? Yes or no? Do you all agree with me or not?
Yes.
I'll go back.
Yes, sir.
I will
Yes.
go back. I will go back. Just wait. Don't worry. Okay. We have already seen the controllers before, isn't it? So this is the PI controller. This is the PI controller. What is the transfer function for the PI controller? Kc 1 plus 1 upon tau is. Now this, remember, if I expand this, what I'm going to get? I'm going to get Kc plus Kc divided by tau is. Do you all agree with me?
Yes, sir.
Yes, sir.
Yes.
Yes, sir.
Now this first term Kc is corresponding to proportional part. So what will be the part corresponding to the integral action?
KC by
Will be Kc divided by tau is. Yes or no? Correct or not?
Yes, sir.
Remember,
Yes.
if I expand this, what I'm going to get? If I expand this, I'm going to get Kc plus Kc divided by tau is. Now the first part, which is Kc, is corresponding to the proportional part. So what will be the part corresponding to the integral part? It will be Kc divided by tau is. Yes or no?
yes.
Yes, sir.
So see, this is the expression for PID controller. If I expand this, what I'm going to get? I'm going to get Kc plus Kc divided by tau is plus Kc into tau ds. That is what the three parts I'm going to get. Proportional part will be just Kc. Integral part will be Kc divided by tau is, and the derivative part will be Kc tau ds. Do you all agree with me or not?
Yes, sir.
Yes.
Yes, sir.
Yes, sir.
So the same thing we are using here. We are using the same thing here, isn't it? Now let's look at the integral part. So see, here I am not using PI controller. I am only using the integral controller. Look at the term written here. It is written that only the integral controller. We have not written proportional plus integral. We have not written that. We have only written the integral controller. So that means the GC will be what? GC will be Kc divided by tau is. Do you all agree with me?
Yes, sir.
Yes. Correct or not? Okay, now let's do the same analysis what we have done earlier. There is a process which is a first order process. Again, we are assuming a servo problem. Servo problem means what? The disturbance variable is 0. So only the set point is changing. So in this particular equation, this d of s is 0. Only the YSPS is changing. So that means only this part is there. This second part is not at all there. So now we are going to put GP, GF, GC in this entire equation and see what type of expression we get when my process is a first order process. So GP is given as Kp divided by tau PS plus 1. So that is a first order process, isn't it? So I can put this GP in this particular equation. So that becomes Kp divided by tau PS plus 1, isn't it? And then GC will be given by what? GC is given by Kc by tau is. So that is what we have obtained, Kc by tau is. And GF is just 1, isn't it? So that is just 1 here. Similarly, divided by 1 plus Kp Kc divided by tau ps plus 1 into tau is. This is what I am going to get because GM is also 1. So this GM and GF is 1. So with that, this is the expression we are going to get. Do you all agree how we have written this? Hello?
Yes, sir.
Again, now I can simplify this. How we can simplify this? This denominator is, let's say, this tau ps plus 1 into tau is. If I multiply numerator and denominator, what I'm going to get? I'm going to get Kp Kc divided by tau p tau y s square plus tau is plus Kp Kc into YSPS. This is the expression I'm going to get. Now, this expression is interesting. Why interesting? Because unlike the previous case, remember, in the previous example, when we use the proportional controller, the order of the system remains the same as that of the process. Do you all agree? Yes or no? Earlier, when I had a first order process, my overall system was also first order, even with the feedback loop. But unlike that, here, I started my original process is a first order process, but my overall process with a feedback loop, with an integral controller, actually becoming a second order. Denominator is having a square. Do you all agree with me or not?
Yes, sir.
Yes, sir.
Isn't it? So my process, first order process is there. My actual process is first order, but actual process, even though the actual process is first order, but my overall response of the system is second order here. And this particular expression I can represent in a usual form. So what we have to do? We have to divide by Kp-Kc. If I divide by Kp-Kc, what will be the numerator? Just 1. And here the denominator will be tau p tau y divided by Kp-Kc s square plus tau y divided by Kp-Kc s plus 1. So this is a standard form. This expression is a standard form. Now in this particular expression, now I can represent what is tau dash. Tau dash will be what? Tau p tau y divided by, so under root of tau p tau y divided by Kp-Kc. That is what is going to be tau dash. Yes or no? And so tau time constant in this case will be tau p tau y under root tau p tau y divided by Kp-Kc. Similarly, the zeta comes out to be 1 by 2 under root of tau y divided by tau p Kp-Kc. This is what I'm going to get if I compare this particular expression with a standard expression. Standard expression will be what? YSP divided by tau square s square 2 zeta tau s plus 1. So I can find out what will be the tau and zeta from this expression. Do you all agree?
Yes, sir.
Yes,
Is
sir.
it clear to everyone? Please ask question if something is not clear. Is it clear to everyone?
Sir, I have some questions.
Please ask. Please ask.
Sir, if the epsilon is there, if the process is overdamped, what does tau represent in that case?
If the process is overdamped.
Overdamped.
Okay. So if
Yes.
the process is overdamped, in that case, there is no natural period of oscillation. Correct. There is no natural period of oscillation.
Yes.
So this concept of natural period of oscillation comes only in case of underdamped. If your question is with respect to that, is it?
Yes, I want to ask only that.
Isn't it? So in that case, there is no natural period of oscillation. In that case, the tau, okay. So in that case, you can connect the tau with the rise time or the settling time. You can connect it with the settling time or a rise time. Remember, I'm not sure whether I have derived the expression for a rise time. It's not derived here, but still I will try to give you some. It's a good question, very, very good question, and I'm happy that you have asked this question. Okay, what is rise time? Rise time is a time used to characterize the speed of response. But what is the rise time? Rise time is nothing but the time when you first time reach to the ultimate
Maximum
value.
value.
Ultimate
Ultimate
value
value.
here, isn't it? Ultimate value here. Okay. Now, if your process is, let's say, overdam, if your process is overdam, in that case, the rise time will be important or a response time will be important. Can anybody tell me? It's a really, really interesting question. Which will
Response
be
time.
response time is a more important. Rise time is not important in that case. Why rise time will not be important? Because if your process is, let's say, overdam, if your process is overdam, in that case, you may reach to the ultimate response or may not reach to the ultimate response, isn't it? But your response time is nothing but what? Response time is the time when you reach to a plus or minus 5% of the ultimate response. You will definitely reach to this. So response time makes more sense. Now, if you calculate, response time for a overdam process, if you calculate a response time for a overdam process, you get a very interesting equation. We have not derived anywhere in the slide. In fact, that was one of the question I have given in my exams earlier. You all can derive that. It's a really interesting question, particularly when you are calculating the response time for a overdam process. Okay. You will find that the response time for the overdam process is actually function of two things. One is zeta as well as tau. So when you are looking at the response time and overdam process, actually the zeta and tau both are relating with the speed of response in that case. Okay, is that clear?
Yes.
Isn't it? So maybe you have asked the question whether it is related to the speed of response indirectly or not. The answer is yes, only in the case of overdam. But that, so see, why we don't want to directly say that it is the speed of response, because it is also related with zeta. Is it clear?
Yes.
Okay. So please try to derive that expression. It's a really interesting expression. I have not derived in any of my slides, but in fact, the information which I am giving you, that was one of the questions I have given earlier. All right, please go ahead. Is there any more question? Hello? Is there any more question?
Sir, when we derived the time constant for the P controller, we compared it with the time constant of the first order process. Does it really give any insight to compare the second order process time constant with the first order process?
So time, oh, that is what I'm saying. So time constant, if you are comparing for the under dam process, then you can directly compare. Why? Because then it is kind of giving you what is the time elapsed between two peaks. That comparison becomes direct for a under dam process. But for a over dam process, second order over dam process, it is somehow related to the speed of response or a response time, but that effect is actually colluded in the sense that zeta is also impacting. It's not just the time constant which is impacting there. Okay. But when you are talking about the first order process, speed of response is only related to the time constant, not any other factor. So there, if you are comparing the impact, uh, the direct comparison is there. Is that clear?
So, but in
Hello?
under process, the natural time period of oscillation doesn't give the speed of the process, right? The response time would be more
No, no.
preferable for that.
Okay, so that in some way give the speed of response. Why? I am telling you why. Just wait. So in a under dam process, the lower is the value of natural period of oscillation. What it means? What it means? These
The earlier
peaks
it will
are
reach to.
these
Yes, yes,
peaks are
correct.
close to each other. Correct.
Yes,
isn't
sir.
it? The time between these two peaks is lower. Even though it is not directly giving in the information, but in some way it is related to the speed of response, isn't it? Lower is the natural period of oscillation. Higher chances is that you will be settling to a ultimate value faster. Yes or no?
Yes.
Okay, so in some way it is related to the speed of response. I am, that is why I am saying I don't want it to say directly the speed of response, because there the impact of zeta is also colluded. It is not just the time constant. Both are impacting. Okay. But direct comparison with respect to the first order process can be there. In the first order process, the speed of response only related to the time constant. That's it. Okay. Make sense?
Yes, sir.
Okay. All right. So we are here. Now here the interesting, observation here is my time constant here is tau p tau I divided by kp kc, isn't it? And also my zeta is given as 1 by 2 under root tau I by tau p kp kc. So you can see that both tau and zeta depends on the controller parameters. What are the controller parameters? Kc and tau I. Remember, Kc and tau I are the controller parameters which are in your hand. You can change Kc and tau I. So by changing the Kc and tau I, you can make your system response under dam, over dam, critically dam. All possibilities are there. Do you all agree with me or not? Correct or
Yes.
Yes,
not?
sir.
Yes, sir.
Another interesting thing here is my original process was first order, but my overall response is what? Overall response is second order. And as the order increases, what happens to the speed of response? As the order increases, my system response becomes more sluggish and delayed. That means my actual process response is faster, but with a feedback control loop, now my response became sluggish. Do you all agree with me or not?
Yes.
Correct or not?
Yes,
Yes,
sir.
sir.
Remember, my original process was first order, but with a controller, PI integral controller, I got a second order process. So clearly the order is increased by 1. And as the order increases, my speed of response becomes slower and sluggish and delayed, isn't it? So since the order is increasing, I can safely say that my speed of response became sluggish and delayed. Do you all agree?
Slow.
Correct? Yes or no?
Yes.
Okay. Now
Yes.
another interesting observation in this. Another interesting observation. This is the expression we have obtained. Look at here, there is no Kp in the numerator. See, when we have simplified this expression, there is no Kp in the numerator here. Unlike the previous case, see, unlike the proportional controller, in the proportional controller, we always get the Kp dash in the numerator. Unlike that, in this particular case, there is no Kp here in the numerator. So what will be the ultimate value when I am having a step input of magnitude unity? What will be the ultimate value here? What will be y at t tends to infinity?
1.
1.
Y at t tends to infinity will be 1, because this YSPS will be 1 by S. I can apply the final value theorem. So that becomes what? Limit S tends to 0, S into YS. So that S will get cancelled out with 1 by S here. So that is nothing but what? We have to put S equals to 0 in this remaining part. If I put S equals to 0 in this particular equation, what will be YT? YT t tends to infinity. It is just 1. Correct. Yes or no? Not clear to anyone? Hello? Not clear, my friend? Yes or no? Please say. Unless you say, nothing will
Yes.
move. Please say. Okay. So the same thing done here. See, you can see we can apply the final value theorem. If I apply the final value theorem, this 1 by S will get cancelled out with this S, and then we have to put S equals to 0 in this entire expression. So this term will become 0. This term will also become 0. We will get Y at t tends to infinity just 1. This one will be remaining. Yes or no?
Yes, sir.
Yes, sir.
Now what will be the
Yes,
offset?
sir.
What will be the offset? New set
So,
point minus 1. isn't it? New set point here is 1 and the ultimate value is 1. So 1 minus 1 is 0. So what we are concluding? When I am having the integral control action like this, my offset is actually becoming 0. So what it means? It means that whenever we have an integral control action, our steady state error becomes 0. That is what we have concluded in the starting lectures. Remember, when we had an integral control action, our offset becomes 0. And we are mathematically proving now that whenever we have an integral control action, my offset indeed becomes 0. Do you all agree?
Yes,
Make
sir.
sense?
Yes, sir.
So that is what we have concluding here. So see, you can see that what conclusion we can draw here is the closed loop response depends on the values of the controller gain Kc as well as tau I. So as you can see that as the value of tau I decreases or the value of Kc increases, my system response becomes from over dam to under dam, and as again increase the value of Kc, it becomes more and more under dam. Similarly, if I decrease the value of tau I, you can see that my system response becomes over dam to under dam, and further if I decrease the value of tau I, it becomes more under dam. So more under dam means more oscillations. And in all cases, I am actually reaching to the ultimate value. But unlike the previous plot here, see, in all the cases, we are not reaching to the ultimate value. This graph and this graph, there is a significant difference. What is the difference? Here, all the plots are reaching to the ultimate value. Here, look at with the proportional controller, none of the graph is reaching to the ultimate value. Is it clear to everyone, the difference?
Yes, sir.
Sir, please repeat.
Okay. So see, here when I am using a proportional controller, remember this is the graph when I am using a proportional controller, I am going back, isn't it? So when I am using the proportional controller, you can see none of the graph is reaching to this ultimate value, which is shown by a dashed line. Whereas when I am using an integral control action, now this is the integral control action. With the integral control action, you can see all the graphs are reaching to the ultimate value. And as I increase the value of Kc or decrease the value of tau I, my system response is becoming more and more oscillatory. Is it clear to everyone?
Yes, sir. Yes, sir.
Another conclusion here is as the Kc increases or zeta decreases, the response becomes sluggish and overdamped. So you can see that as the value of Kc decreases, you can see that the system is becoming more and more overdamped. So if I increase the value of Kc from overdam, it becomes underdam. Underdam means you will have oscillation. So that means speed of response is becoming faster, but it comes with the cost of oscillation or a decay ratio increases, isn't it? Again, in this case, you can see that Kc and tau I are nothing but the controller parameters. So increasing the control action means what? Either you increase the Kc or decrease tau I. Remember, in this case, if you look at the expression here, increasing the control action means what? Either you increase the Kc or decrease the tau I. Do you all agree with me or not? Increasing the control
Yes.
action means what? Either I increase the Kc or decrease the tau I. So as I increase the control action, my system response becomes more and more faster, but that comes with the cost of oscillations. That is what we are trying to conclude here. System is going to become more and more sensitive, and therefore there will be more and more oscillations as we increase the value of Kc or decrease the value of tau I. Do you all agree with me? Hello?
Yes, sir.
Yes.
Yes, sir.
Okay, now let's look at the impact of derivative control action. This is also interesting because each of these control actions are actually shaping the entire philosophy of using PID controller. Why proportional action should be used, why integral control action should be used, and why derivative action should be used. Of course, we have qualitatively discussed in the starting classes. Remember, we have discussed why proportional control action, why derivative control action, why integral control action. All these we have qualitatively discussed. But now we are trying to derive the expression. We are trying to analyze that in terms of mathematical equation. And we are confirming whatever qualitative discussion we had at that time is indeed true in terms of mathematics. It is not just vaguely described there. There is a reason why we are saying that the proportional control action is the strength of the controller. Why in the integral action eliminates the offset, and why derivative action makes your system response stable. There is a reason for that. It's not just qualitative description. It comes from the mathematics. It comes from the mathematical expression. And those mathematical expressions we are trying to derive here, and we are trying to appreciate more. Is it clear to everyone why we are doing this? Hello?
Yes.
Yes, sir.
Okay, now
Yes.
let's look at, we will start with the same expression. We are purposefully using the same expression and same situation. Why? Because we wanted to segregate the impact of each of these modes. How this proportional action is going to impact, how this integral action is going to impact, how this derivative action is going to impact. That is why you can see that the same system we are using. This is the same expression I'm coming back, I'm using again and again, isn't it? So the same expression ys is given as gp gf gc divided by 1 plus gp gf gc gm ysps plus gd divided by 1 plus gp gf gc gm d of s. We are again assuming that gms and gfs is just one. So that means we are neglecting the dynamics of measurement unit and final control element. But now the controller we are using is what? Now the controller we are using is a derivative control. I am not saying PD. PD is nothing but what? Proportional derivative. Here I am saying only the derivative control. Of course, in a physical case, you will not be using only the derivative control. There is a drawback with respect to that. And I said at that time itself, isn't it? You can use integral control action alone. You can use proportional control action alone, but you will never use the derivative control action alone. There is a reason for that. Okay. So in this case, even though this cannot be used physically, but we just try to understand how this is going to impact my response. That is why I have taken only the derivative action here. Typically, the derivative action is always associated with the proportional. Always associated with the proportional. Why? Because the derivative control action, if your error becomes constant, your control action is going to become zero if you use only the derivative. That is the reason why derivative action is never used alone. Do you all agree with me or not? Yes or no?
Yes.
If my error becomes constant, it's not zero, it is constant, let's say. In that case, derivative control action becomes zero. That means your controller becomes redundant. That is the reason why derivative control action is never used alone. Okay. People may ask this question. This is commonly asked question in the interviews. Why derivative action is never used alone? You can use integral action alone. You can use proportional action alone, but you never use derivative action alone. Because whenever the error becomes zero, your derivative action becomes zero. That means your controller is going to become redundant even if there is a positive error, but constant positive error. Constant positive error means derivative action is zero. What is derivative action? It is actually calculating the slope of the error curve. If your error is constant, what is the slope of the error curve? Zero. Yes or no?
Zero.
So you get the philosophy why derivative action is not used alone. Is it clear to everyone?
Yes, sir.
Okay. So let's start with the same system. Our system is first order system. Gp is given as Kp divided by tau ps plus 1. Again, we are just for a simplicity, we are assuming that there is no disturbance. We are only looking at a servo problem. Remember, all the cases we have derived only for a servo problem. But you can derive all these cases even for regulatory problem. And you will get the same conclusion, by the way. Okay. We are not deriving for the regulatory problem only sake of saving the time. But you will get a similar conclusions. Is that clear to everyone? Only the servo problem we are looking at all the time. We are not doing it for a regulatory problem, not because you will get a different conclusion, only because we wanted to save some time. You will get the same conclusion even if you are looking at the regulatory problem. Okay. So servo problem we are looking at, that means only this part we are going to look at little bit in more detail. I can put GF and GM equals to 1. And then GC will be taken as just KC tau ds. So GC is replaced by KC tau ds, whereas GP is replaced by KP divided by tau ps plus 1. So this is the expression I'm going to get. I can simplify it. If I simplify this, then we are going to get KP KC tau ds divided by tau p plus KP KC tau ds plus 1. Okay. Now, in this particular case, what conclusion we can draw? My process but with a derivative action, my process still remains the first order. Remember, this particular expression is also a first order process, isn't it? The only difference here
Yes,
is
sir.
now the time constant has increased. Earlier time constant was just tau p, but with the derivative control action, my new time constant of the entire process is tau p plus kp kc tau d. So my time constant increased. So what it means? When we increase the time constant, what it means? Anyone? If I increase the time constant, what it means? My system response is going to become slow.
Slow.
Isn't it? Again, if I increase the value of Kc, this time constant is going to increase further. And therefore, with the increase in the time constant, my process is going to become more and more slow. Is that clear to everyone? Another interesting thing is there, but we will not come back to this discussion. This discussion we will come back when we will look at the stability. Remember, there is a S term in the numerator. Remember here the Kp, Kc, tau ds, this S additional S term is coming in the numerator. Yes or no?
Yes.
See, here there is no S term in the numerator, but here you are getting additional S term in the numerator. Even though I am drawing the conclusion, but these conclusions I am drawing only based on the denominator, but that is only the half of the explanation. There is another half which is completely dependent on this S present in the numerator. And this S has a very significant impact. I will not explain now. I will explain this S term when we will look at the stability. Then you will appreciate why this S term is in the numerator is extremely important. I can only say qualitatively now that whenever you have any additional S term in the numerator, that leads to the stability. That leads to the stability. And we will prove this fact. As we go ahead, we will, after 2-3 classes, we will look at the stability and you will see this S term in the numerator has a significant impact on the response. I purposefully not discussing that now because you will not appreciate now. When we will look at the stability, then you will see that this S term in the numerator has indeed a significant impact on the stability. Okay, is it clear to everyone?
Yes.
Okay, now this is for a first order process. Let's extend this discussion on a second order process. Same, everything is same except that the GP will be a second order process. So the same thing we are doing. Just this GP becomes second order. Again, I can look at the servo problem, isn't it? So I can put this GP as the second order transfer function, and then the KC will be GC will be KC tau ds, and the rest all the transfer functions are 1, isn't it? So with that, this is the expression we are getting. We can simplify this. If I simplify this particular expression, what we are going to get? We are going to get Kp Kc tau ds divided by tau square s square plus 2 zeta tau plus Kp Kc tau ds plus 1. This is what we are going to get. Now this is really interesting. Why I'm saying this is really interesting? Because if you look at the denominator, the time constant of the second order process, see, this actual process is second order. With the derivative control, we are again getting the second order response. The only difference here is the time constant remains the same. See, time constant tau remains the same. So what it means? It means that the natural period of oscillation is going to remain the same, isn't it? Look at the zeta here. Zeta value actually increased here, isn't it? Earlier I had a zeta value equals to zeta, but with this additional term, now my zeta value will be definitely higher than the actual zeta. So that means this zeta dash will be definitely higher than the zeta. Do you all agree with me or not?
Yes.
If this zeta dash is greater than zeta, what it means? It means that your actual process might be under damped, but with a derivative control action, it will become a over damped. Is it clear? Your actual process is under damped, but with a derivative control action, it becomes over damped. So what it means? Your system response is going to become sluggish, but that comes with the advantage of eliminating the
Oscillations.
oscillations. So you can see you can see that whenever proportional controller is proportional and integral controller is there, integral action is going to add the oscillations. But when you add the derivative control, it actually eliminates the oscillations, isn't it? So you can see that whenever you have more oscillations, there is a tendency to make the system unstable. As you increase the oscillations, there will be a point when the oscillations are going to increase, isn't it? And it will grow instead of dying out. And that is the point where you get the response which is unstable. Correct. But with the derivative action, you are actually eliminating the oscillations. So that means you are making your system more stable with the derivative action. Is it clear?
Yes.
More interesting observations you will get with respect to this when we will look at the stability. In fact, see, remember I said derivative action is primarily for stabilizing the process. So you will appreciate its concept more when you look at the stability part, isn't it? Remember, here also we are saying only the half story. The remaining half is with respect to the S which is present in the numerator. That we have not said anything so far. Okay. Is it clear to everyone what I'm saying?
Yes, sir.
Okay, how much is the time now? So 8:46. Can I take 10 minutes?
Yes, sir.
10-15 minutes I can take. Okay.
Yes,
Okay.
sir.
So please say, is there any problem, any confusion, any question, queries? Please ask. Okay, let me go to the next slide. Now this is the new topic. So far what we have studied. If you go back and look at what topics we have covered in this particular course, we started with the question. Remember in the first slide I had that question that why process control, isn't it? We started from there. Why process control is required? Why process control is required? We said there are three requirements for which the process control is required. First requirement is to negate the effect of the disturbance on the process, to make the inherently unstable process stable, and the third requirement was to make the process profitable. These are the three main requirements for which the control is required. Then we said, in order to have a controller, in order to have a control, you need to know the system. That is where different mathematical concepts comes into the picture, like modeling came, Laplace transform came, isn't it? uh, uh, Degree of freedom came. All these concepts, linearization came. All these concepts came because we wanted to know the system, isn't it? So we wanted to know the system means what? We wanted to represent the system in terms of equations, isn't it? Then once we have done that, then we said, okay, we know the system, we know what we wanted to do. Then the question was how we can do that. So there we have discussed feedback control system. We said, okay, I wanted to control the system. I also know the system in terms of equation. Now, how I can use this knowledge of the equations in order to achieve my aims. And what are my aims? To negate the disturbance, to make the unstable process stable, or to make the system profitable. In order to achieve this, how I can use the knowledge control system. If there is change in the measuring, at the correct, then we how to achieve the feedback system. There will be different controllers. There is a proportional controller. So proportional control means we are going to add the external intervention proportional to the error, or proportional how much my system is messed up, isn't it? How much my system is messed up, based on that, proportional to that, I am going to apply the control action. That is something called as proportional control. We said that with the proportional control action, which is logical, but with this logical controller, I am not going to eliminate my steady state error completely. Why? Because I am applying the control action which is actually corresponding to a system which present at a time earlier, isn't it? Because all the systems will have some error lag associated with that, isn't it? So my control is not going to be perfect. So I will have steady state offset with the proportional controller, isn't it? So then we said we will apply the integral action. So integral action will keep on increasing the control action till the error is eliminated. So proportional integral action is going to eliminate the error. But proportional integral action is eliminating the error, but it will also add the oscillations. And in order to eliminate the oscillation, I will need to have derivative action, and therefore the PID controller came, isn't it? Now the question here is, out of these different choices, there are, when I'm designing the feedback control system or feedback controller, the three important questions we are asking ourselves is, out of different choices of controller, which controller I should select? Whether I should use P, whether I should use PI, whether I should use PD, whether I should use PID, isn't it? And this question is very, very important. Why? Because depending on what you are selecting, the complications are going to vary. For instance, proportional controller, only one parameter is there, isn't it? It is easy to obtain that parameter. Remember, all these controllers, you have to give the value of their parameters. You have to specify the value of Kc in proportional controller. You have to specify the value of Kc and tau I in Pi, isn't it? And you have to specify Kc, tau I and tau D in PID. So these are the variable values which you will have to find out. And you will have to find out the appropriate values of these. A thumb rule says the simplest controller which is working for your system is the best. That is the thumb rule in the process control. Don't make your control system unnecessarily complicated. And that is the reason the proportional controller is used in a level control. Why? Because in level control, you don't require a sophisticated PID controller, isn't it? Servo problem, there is an offset 0. And in a regulatory problem, your offset is -1 by Kc. You can have slightly higher value of Kc and you are done. Don't need to make your system unnecessarily complicated by using PID. It is kind of, okay. एक बहुत ही अच्छी बात कही जाती है, पता है, रावण को मारने के लिए ब्रह्मास्त्र चाहिए, छोटे मोटे सैनिक को मारने के लिए ब्रह्मास्त्र नहीं चाहिए. You need ब्रह्मास्त्र only to kill the Ravan, not for an ordinary soldier, isn't it? Don't use the PID unless it is required. Does it make sense to everyone what I'm saying?
Yes, sir.
You go to the complicated controller only and only if it is required, not otherwise. If you go to a complex PID controller, you need to tune 3 parameters. It is not going to be easy. It is not going to be easy. I will come back to that. How to get the parameters for these different actions. So the first question which we are trying to answer here is, which controller is the best? P, PI, PD, PID. A simplest answer here is, select that controller which is simplest enough to solve your problem. In a very layman's way, that is the answer. Don't make your control system unnecessarily complicated unless it is required. Okay. Let's say you have answered the first question. You have answered that whether you are using P, PI, PD or PID, you have answered that question. The next question is how you are going to obtain the values of the parameter. So P will require Kc, PI will require Kc and tau I, PD will require Kc and tau D, PID will require Kc, tau I and tau D. How you will get the values of these parameters? That is something called as controller tuning. So how you are going to tune your controller? That is the second question. There are different ways of tuning. We will see some methods. There are some thumb rules also, isn't it? We will look at the thumb rules. We will look at some complicated way of tuning the controller also, isn't it? And there are some of the ways where you can tune the controller parameters empirically. Okay. All these tuning methods we are going to look at little bit in more detail as we go ahead. Is there any question? भैया आप थोड़ा सा अपने आप को म्यूट कर लो if there is no question. my sincere request. And I'm extremely sorry. If I'm taking more time. Please forgive me. I wanted to take only 2 classes instead of 3. Remember, we are going to miss today's class. We have already missed today's class in the morning. We are going to miss tomorrow's class, and most likely we are going to miss Friday's class. So I wanted to take only 2 extra classes today and tomorrow online. Okay, please accept my apology for taking the online class. I would love to take the physical class because there the most learning happens. Here online, only few people pay attention, many people don't pay attention, and that is why I am again and again requesting all the students, please pay attention. If you have any question, ask me. Ask me any question. I will be happy to answer any of your questions. Okay, that will only make me happy. Why? Because I will study more. This course I am taking year after year, only and only if you provoke thinking process is not going to add anything for me. Okay, so please ask questions. Okay, well, so second question is how to tune the parameters. We will come back to this question, how to tune the controller parameter. We will look at some of the methods of tuning the controller parameters as we go ahead. Now the third important question is what performance criteria we should use for the selection and the tuning of the controller. Here we are saying the controller tuning, but controller tuning based on what? There should be some aim in controller tuning. Whenever I am tuning something, okay, in machine learning, whenever you are trying to do the training of the machine learning algorithms, there is some aim, isn't it? The aim is your machine learning model prediction should be nearly the same as actual prediction. That is what. So in a way, you are trying to minimize the error between your actual prediction and the predicted by the model, isn't it? Similarly, in this particular case, what is the final goal which you are trying to achieve in the controller tuning? Are you looking at minimizing the error, or are you looking at minimizing something else? Isn't it? Typically, the performance criteria could be different here. For instance, you might be interested in minimizing the maximum deviation as small as possible. So what is maximum deviation? Tell me, anyone. What is the maximum deviation? If I'm saying maximum deviation, what could be the maximum deviation? So maximum deviation is nothing but what? Maximum deviation nothing but overshoot, isn't it? Do you agree with me or not?
Yes.
Steady state error. So here maximum error we have talked about. What will be the steady state error? Steady state error is nothing but offset. Okay. We might be interested in minimizing the settling time. Isn't it? If I'm having an oscillatory system, it will settle to a final value after a long time. I wanted to reduce that time. Or I could have slightly more complicated objective or complicated performance criteria like minimize the integral of the errors until the process has settled to a desired set point. So there can be different performance criteria that can be used for controller tuning. Okay. Now this is a typical example is given here. For instance, let's say this is the regulatory problem. So regulatory problem, if I'm giving a step input in the disturbance variable, if there is no control, what will happen? My output will also kind of increase to a new value, isn't it? And since I'm looking at a second order process, that's why I'm getting a sigmoidal curve. So this is the uncontrolled process. So ultimately regulatory problem is what? What is the desired value in a regulatory problem? What is the desired value in a regulatory problem? Anyone? In a regulatory problem, desired value is 0, isn't it? This yt, remember all these variables are given in a deviation form. That means this yt, I'm interested to keep this yt value to 0. Yes or no? That is what the regulatory problem is. So regulatory problem is what? Disturbance variable is changed by 1. So if the disturbance variable is changed by 1, it should not impact my actual output variable. That means this yt should remain to the value of 0. But actually, if there is no controller, if there is no control, in that case, this yt will increase from 0 to some value, isn't it? That's why this uncontrolled process is shown like this. Is it clear to everyone? There's a very small difference between regulatory problem and a servo problem. I'll again come back. Just wait. So why I am coming back to this particular thing is, otherwise you'll miss the point. See, there is a comparison between servo problem and regulatory problem. In servo problem, my desired value is this dotted line. That is the desired value. Why? Because my set point changed. Set point change means what? My output should also match to a set point. That's why I am interested to reach to this point. But in a regulatory problem, what is changed? In a regulatory problem, actually my disturbance variable changed. And therefore, my desired value is not this dotted line. My desired value is this 0 line. There is a difference in servo problem and regulatory problem. We don't observe that. Very likely we miss these small points unless we pay attention. Okay. So regulatory problem, my desired value is this 0 line, not this dotted line. In a servo problem, I am interested in reaching to this dotted line. Why? Because my set point changed to 1. And that is why I wanted to reach to the 1. In a regulatory problem, my disturbance variable changed to 1. But I'm not interested to track the disturbance variable. I'm interested to negate the impact of the disturbance variable. And therefore, my aim is to reach to a 0 line, not to this 1. Is it clear to everyone?
Yes, sir.
Okay, so that is what is shown here. So see, this is a regulatory problem. See, clearly written regulatory problem. So when I do not have a control, I am reaching here. But ultimately, I am aiming at reaching this 0 line. But when I am using a proportional controller, what will happen? This particular process is overdamped. But when I'm using a proportional controller, because of the control action, my system response is going to become oscillatory. But it will settle to a higher value instead of settling to a 0 value. And this difference is going to be offset. Do you all agree? Correct? Because proportional
Yes.
controller never gives you a perfect output. It will have offset. And therefore, it will not settle to a 0 value. It will have a steady state error. That is why this line is not settling to a 0 value. But if you look at a proportional integral controller eliminates the offset completely because of integral action. And therefore, proportional integral controller is going to settle to a value 0. But it will have more oscillations compared to this. And when you are using a PID controller, it will again settle to a 0 value because of integral action, but because of derivative action, these oscillations are going to decrease. And therefore, in a PID controller, you can see there are less oscillations compared to PI controller. So this particular figure is not drawn arbitrarily. It is drawn with some logic, isn't it? Please don't look at all these figures. There is a reason why these are drawn like that. Okay. Is it clear to everyone?
Yes.
Yes.
Yes, sir.
How much time? It's 9. So, okay, we will stop here and we will continue from this point in the next class. Please go through the slides which I have already shared at Scoop, isn't it? Please get the printout of that and go through all the slides. There are some mistakes here and there because the slides I have prepared last year only, isn't it? So that is why some mistakes are there here and there. And also, if you find some mistakes, please tell me so that I can correct it. Other than that, again, I apologize one more time for doing this class online and also slightly extending beyond the time. Okay. So with this, let's stop here unless you have any question.
Sir, I have one question.
Please ask.
Sir, can you go one slide back, one of the questions? Sir, why have you written here integral controller when it is a derivative controller behind GC?
Derivative, please repeat the question. What is the question?
You have written that it is integral controller behind the GC.
Where I have written? Show me.
Second line.
Acha, this Okay. Sorry, this should not be. This is the mistake. This is the mistake. Thank you. Thank you for pointing. This is not integral controller. It's a derivative controller. Thank you for pointing. Okay.
यस सर, एक और क्वेश्चन है सर.
बोलिए.
सर वो जब आपने इंटीग्रल कंट्रोलर इंट्रोड्यूस किया था उसमें आपने टाउ को रीसेट टाइम कहा था, एक बार वो बता दोगे रीसेट टाइम क्यों कहते हैं?
हाँ, we'll go back. Just wait. We'll go back. And I'm really happy that students are asking the question. Please have the habit of asking the question. I will never take your questions in a wrong way. You ask as many questions as possible. I will only take them in a positive spirit. Okay, so please ask. Please ask. This is the slide. Okay, please ask the question. So why we are calling the tau I as a reset time? Is that the question?
Yes.
Okay. Let's take a very simple case here. This is the equation, fundamental equation for the PI controller. Let's take a very simple case of constant error. Let's say epsilon is constant. Okay. So in that case, what you are going to get? Kc epsilon t into t, isn't it?
Yes, sir.
Correct. Now, if the time is exactly same as tau I, in that case, this particular term is going to become what?
1.
No, this will become Kc epsilon t. That's it.
Yes.
This tau
yes,
I
yes.
will get cancelled out with this t, isn't it?
Mhm.
Correct. So, but the Kc epsilon t is the same output you are getting from the proportional part. Correct. Kc epsilon
So
t
what
is
does
the
resetting here mean?
So I'll come back. So what it means is proportional action is giving me Kc epsilon t as a output, and the integral action will also going to give you the output which is equals to Kc epsilon t when the time t equals to tau I. So what it means? It is resetting the same output when t equals to tau I. Of course, that you can get only when the epsilon t is constant, otherwise not. Correct?
Yes.
So that is why this tau I is called as a reset time, because you are going to get the same amount of output as that of proportional action when t is equals to tau I, provided that epsilon t is constant. That is why it is referred as reset time. Is it clear? Still not clear? Hello, am I audible? Hello, am I audible?
Yes.
Yes, sir.
Is
Sir,
it
तो फिर
clear or not
इसमें
clear?
ऐसे कर सकते हैं कि मतलब कि the error is still constant even after applying the action of Kc epsilon.
No.
That's why.
Typically, the error is not constant. Typically the
Yes.
error is not constant. Okay, error will vary, but we are trying to understand this particular controller in a very simple way. We are saying that let's say the error is remaining constant. How this particular tau I is going to impact. So we are saying that if this error is constant, this action will be exactly same as proportional action when the tau is same as tau I. So it is nothing but the time when your output is resetting to a exactly the same as the proportional value. So it becomes double. The proportional action is going to become double when the time is equals to tau I. So it's going to become double in 1 tau I. It is going to become triple in 2 tau I. It is going to become 4 in So as your tau t is increases with the multiple of tau I, the proportional action is going to increase with the same number. Is that clear? That is why it is we are calling it as a reset time.
Yes, sir.
Isn't it? That's why it is written like this. See, CS plus KC in 0, but when it becomes tau I, it becomes double, isn't it? When it becomes triple, when t equals to 2 tau I. So every tau I, it is actually increasing by 1. Is it clear now?
Yes.
Okay, any more question? Any more question, guys? Okay, so if there is no question, let me thank all the participants for joining, and uh, we will again come back tomorrow around the same time. Okay, 7:30 to 8:30, and we might go 10 to 15 minutes extra. And please note that whatever we will cover tomorrow, that will be the syllabus for, up to that will be the syllabus for the quiz. Okay, please read the material carefully. All the rules whatever we had in the minor, the same rule will be applied. That means the exam is going to be open book. Exam will be 2 hours. There will be multiple questions, and questions will be slightly conceptual. So please go through the material. Okay, can we stop here?
Yes.
Okay, so let me download the attendance list and then we will stop. Okay, and let me stop the meeting also. Uh, how to stop the meeting? End the meeting. Okay, guys.